It is time for one of my absolute favorite subjects in the entire CCNA curriculum, and that is ether channels. Because you've heard me moan and complain or bemoan every once in a while about these trunks that we have that we're not using to carry data. Because if I've got available passages between two switches, multiple available passages, I want them all to be used because that's a lot more efficient than just using one of them, right? Makes perfect sense. Well, we did a little bit of that with per VLAN load balancing. We brought both of the trunks into play. For certain VLANs, one trunk would carry the data. For another VLAN, another trunk would carry the data. But what we'd rather do is just kind of leave that alone and bundle all of our available trunks to begin with. And that's all an Ether channel is. It's a logical bundling of physical connections. And it's a 2 to 8 parallel trunks running between two switches. We can bundle fast Ethernet, gig Ethernet, or even 10 gig Ethernet. And we call this aggregation. It's a fancy, schmancy, artsy fartsy way of saying that we're taking some things and we're making one thing out of them. We are combining them. Later in your studies, you'll actually aggregate some routes. You run into that with BGP in particular. But right now, what we're aggregating or putting together are those physical connections. And we're going to see a couple of major benefits here because we use more available bandwidth when we use ether channels than when we don't. And we also avoid some of the delay that comes with the max age and forward delay timers if we happen to lose one of our ports. And we'll see all that in action. I've got some great labs here for you. And I was mentioning aggravation to avoid that. Ports put inside an ether channel should be running at the same speed and have the same duplex settings. And if you don't, the switch is going to scream at you. It's going to let you know immediately there's a speed or duplex problem, but we're going to avoid that by making sure that we obey that rule to begin with. Two major reasons that we love ether channels, two main benefits. And the first one comes with an STP operation that's necessary, but it's still a little bit annoying. And that's the blocking of available trunks that STP performs. Now, I say problem here in quotation marks because it's not a problem because that's what STP is supposed to do. It's just not the best we could do. And we'll see that here live in this upcoming lab. Switches 2 and 3 are trunking over 4 separate physical links now. We're using fast Ethernet 1 through 4 on each switch. The other switches are out of the mix and any and all previous configurations have been erased. So this is what we're looking at. Now, let me hit you with a little pop quiz here before we get too busy ether channeling. We got two switches here. We know one's going to be the root, one's not. But how many of these ports will be forwarding once STP converges? Which, of course, wouldn't take long with a two-switch network. And if that's not hard enough, and I bet it's not hard for you, but also tell me exactly what role each of the ports would be playing. If you need to think about that for a second, go ahead and pause the video because I'm going to bring that up here and we'll go ahead and verify everything. And first off, here's show interface trunk on switch 3. And as we clearly see, all 4 ports are trunking. They're all in auto mode and they're all running .1Q. They're all trunking and they all have the native VLAN of 1, which we like. So let's go ahead. And on switch 2, we have show interface trunk, exact same thing going on. So to check out the port memberships then, and their port roles, we've got to run show spanning VLAN. And I'll run that on 1 to begin with. Now this is our root switch and we know the different ways to tell that. And we also notice that all 4 of these ports are forwarding because all your ports on the root are going to be forwarding. And their role is designated. They are designated ports. So far out of our 8 ports, we have 4 forwarding and 4 designated ports. Let's hop over to switch 3. And on our non-root, 3 of them are blocking. They're alternate ports. And we know the deal here. The non-root is going to pick a root port. We went through that process. Then it's chosen one. The other ports all go into blocking mode. And the root port will be the only one in forwarding mode. So the end here, I've got an illustration here for you as well. The end result is that we have 5 ports forwarding and 3 ports blocking. And just switch 2 is the root, all the ports there forwarding, switch 3 not the root, and only 1 port is forwarding there. Now, the one issue we have right now, of course, with that is that only that first trunk where they're both forwarding, that's the only one that's going to be carrying data. And the other three are standing by. And again, we love the redundancy and we love the backup, and that's all fantastic. But wouldn't it be great to go ahead and combine them and use them all at one time? That would be fantastic. And when we configure an Ether channel, we can choose to use all 4 of the trunks for data transport. It beats the heck out of using 1. We could do 3, and actually that's what we're going to do first, is put 3 of them in an Ether channel. Now that is a huge improvement in throughput, not throughput, and I'll fix that, but it's not the only reason that we use Ether channels. Right now, if Fast Ethernet 1 on switch 3 goes down, Fast Ethernet 2 will begin to assume the role of the root port. Now that's going to happen really quickly. But while Fast 2 quickly becomes the new root, it doesn't mean that Fast Ethernet 2 is forwarding immediately. It still has to go through the usual STP listening and learning states on the way to forwarding. So for that time period, there will be no trunk on switch 3 that'll be in forwarding mode. And a good way to see that in action is to see it in action. So we're going to actually make Fast Ethernet 1 fail. And we'll let the little messages come up there. And there they go. And you can see Fast Ethernet 2 has already taken over as root. I mean, that takes almost no time at all. The thing is, right now, its status is listening. So if we go ahead and hit it again now, it's already in learning mode, so we're getting somewhere. But right now, we have a total lack of a port that is actually forwarding to switch 2 over on switch 3. So we would like to avoid that delay, and we had a forward there, so we're in good shape. But again, it would be nice if that didn't have to happen. So right now, I will go ahead and reopen that port. And the thing is, with an Ether channel, what's going to happen when a port like that goes down is that the cost of the Ether channel will change, because we're going to see this Ether channel cost change a couple of times. Now we know the default cost for a Fast Ethernet port, root path cost, is 19. So we'll want to compare our Ether channel costs to that, because again, just reviewing, by combining the physical ports into a single logical channel, the bandwidth of the links is combined, and the failure of a physical link inside the channel doesn't interrupt communications. Now the cost of the EC will change, but the availability will not. So there is a lot going on there with an EC and a lot of great benefits. What we're going to do at the beginning of the very next video is put our Ether channel into action, and I will see you there.